Welcome to Level 4, the climb. We are tackling 2D vectors using Coulomb's law and a bit of geometry. Our goal is to find the net electric force acting on charge Q2. Step 1. Solve the geometry. Look at the right triangle formed by the charges. We know the hypotenuse is 5.0 millimeters, and the base is 3.0 millimeters. Using the Pythagorean theorem, we find the vertical side. The distance between Q2 and Q3 is 4.0 millimeters. This is a classic 3-4-5 triangle. Step 2. Identify the forces. Now look at the free body diagram on Q2. Since all charges are positive, they repel each other. Charge Q1 pushes Q2 to the right with force F21. Charge Q3 pushes Q2 downward with force F23. Step 3. Calculate and combine. Calculate the magnitude of each force using Coulomb's law. Once you have both values, use the Pythagorean theorem one more time to find the magnitude of the net force, F2, and use the inverse tangent function to find the angle theta. Pause the video now to try the math yourself before looking at the solution. In this first part of the solution, we focus on geometry and individual force magnitudes. First, let's solve for the missing distance. Looking at the arrangement of charges, we have a right triangle with a hypotenuse of 5 millimeters and a base of 3 millimeters. Using the Pythagorean theorem, we calculate the height, the distance between charge Q2 and Q3, to be 4 millimeters. This is a perfect 3-4-5 triangle. Next, we calculate the magnitude of the forces using Coulomb's law. For the horizontal force, F12, we use the charges of 1 nanocoulomb and 6 nanocoulombs over the distance of 0.003 meters squared. This results in 0.006 newtons directed to the right. Finally, for the vertical force, F32, we use the 6 nanocoulomb charges over our calculated distance of 0.004 meters squared. This gives us 0.020 newtons directed downward. Take a moment to verify these directions on your diagram before moving to the vector addition in the next scene. Now that we have our individual force components, it is time to find the resultant vector. Looking at our diagram, we have a horizontal force, Fx, of 0.006 newtons, and a vertical force, Fy, of 0.020 newtons pointing downward. To find the total net force, we apply the Pythagorean theorem. We take the square root of the sum of our squared components, 0.006 squared plus 0.020 squared. This gives us a net force magnitude of approximately 0.021 newtons. Finally, we determine the direction. By taking the inverse tangent of the vertical force over the horizontal force, we find an angle of 73.3 degrees. Because the vertical component is pulling downward, our final vector is oriented 73.3 degrees below the positive x-axis. Vector addition is now complete.